What else do you want to measure? Angle. Okay, angle's a weird one. And then it's sort of make a wee side thing for angle. And what do you want to use to measure angles in? Degrees. Or do you know what the other one is? Radians. Awesome. I'm going to leave those there for a maths conversation. So we actually do a topic in maths on degrees and radians and why you use them and what the difference is. So I could kill another half hour easily talking about radians, but we'll leave that for a maths conversation. Okay, so just park that one for a moment. It's more of a maths unit than a physics unit. But good call. What else do you want to measure? Energy. Okay, now we're getting into the real stuff. Energy or work is measured in the same thing as energy. Anyone know what we're going to measure? Watts? Joules for energy. Watts. Okay, so it's always a great way. What is a watt? Okay, so I'll put watts down here, and then we'll try and think about what is a watt as we what's what when we come to that. Okay, joule. So the symbol for a joule is a capital J, and the symbol for a watt is a capital W. Okay, so two questions going around in my head. First of all, what's the word that's missing here? And the second thing is, how much is a joule? What do I actually have to do to be doing a joule? Is a pretty important question. So does anyone know what we're measuring watts in? What watts measures? No, so joules measure energy. So what's the thing that's measured in watts? No, it's another one. Where do you hear the word watts? Yeah, it's not actually. Electricity is another one that we've got to bear in mind. So they're doing a whole lot of really good things here. Just let me just write, just so we don't lose it. We're going to need that later on, so we'll keep that on there. So when you talk about watts, you talk about light bulbs and watts. You talk about how much something is generated at the Benmore Power Dam. And I said the word. What was the word, Walter? Oh, okay, power. Yeah. I was trying to play that that game where you've got to try and get people to guess the word without saying the word, and I said it anyway. So power. Okay? So power is measured in watts, and it can be electrical power, but it can be other sorts of power as well. So watt is a more general term. Okay, so let's ask the question of what is a joule? How much energy is actually in a joule? To answer that, we need to go back one step and ask, what is a Newton? Okay, so how much force is 1 Newton? So I've just said that, I rubbed it out from here before, but I said that on Earth, weight, which is a type of force, is equal to whatever the mass is times 10, near enough for this exercise. So my weight is 900 newtons. So 1 Newton is 1/900th of me, which doesn't really help you a lot. Pick up a calculator or your pencil case or something that's about 100 grams, okay? Because 100 grams is 1/10 of a kilogram. If you multiply that by 10, you'll have 1 Newton. Yeah? So it's worth doing. Just find something that you've got lying around that's probably that for me. That's about 100 grams, and just feel it. It is actually worth doing. Just pick something up that's kind of small, and just your headphones, your cell phone, your pencil case, whatever, and just feel it. That's roughly 1 Newton in the ballpark. Yeah, so it's worth it. If you're going to be doing engineering, 1 Newton is not going to do a lot of the time. Yeah, if you're asking questions like, how much force do I need to keep that building up? 1 Newton is not going to be the right answer. Okay, it's going to be a lot bigger. So we end up doing a lot of stuff in kilonewtons and meganewtons, thousands of newtons. But that's 1 Newton, roughly. Yeah? Okay, work requires me to do something with a force. So if I'm doing some work, I'm all over the place, I'll come over here. If I'm doing some work, I'm taking my thing and I'm actually moving it against the force. So the force is downwards. So if I want to do work on this, that didn't take a lot of work. Okay? I'm going with the force, it'll happen quite automatically. I don't have to do anything. So that's not work. That's just letting it go. Okay? That's easy. If I want to do work, I've got to go that way. Okay? So work is moving against the force a particular distance. Okay, so work, I've got two W's here. So this W was weight. But work is whatever force I'm moving times whatever distance I'm moving, as long as I'm going straight against the force. Okay? So if I want to do 1 Newton times 1 metre, okay, so if I'm going to move my 1 Newton, I'm going to move it 1 metre. So the floor is down here, 1 metre is about here somewhere, I guess. I don't know, it's about 1 metre, doesn't it, roughly? Okay, so if I do this, I've just done 1 joule of work. Okay, so 1 Newton, 100 grams, through 1 metre is 1 joule. Yeah? So that's equal to 1 joule. Okay, so 1 joule is 1 Newton metre. Okay, so Newton is the unit as a kilogram metre per second squared. Where did that come from? That's really radical. So Newton, we've decided this is a Newton, there's the kilogram. So what's going to be the unit for this thing? Metre per second squared. So this 10 on Earth, so gravity is measured in metres per second squared. Metres per second, which is a unit of what? What do you think, if I was coming up here somewhere, what would I have in metre per second? No and no. Good try. Okay, let's think about it. We've got metres. Metre per second is a measure of speed, isn't it? How fast my distance is changing. So how fast distance is changing, we call speed. And that's metres per second. I now want speed changing. So what do we call how fast your speed changes? Is your acceleration, isn't it? So that one is acceleration, is metres per second squared, or metres per second squared. Yeah? So, and what I'm telling you is that on Earth, that's always 10. It's constant. It doesn't change. Okay? So if I'm going to get something to accelerate with gravity, it will accelerate at 10 metres per second. So every second it falls, it'll be going 10 metres per second faster than it was at the start of that second. Okay? And metres per second times by 3.6 for kilometres per hour, so 36 k's. So if I let something fall, after 1 second, it'll be going 36 kilometres per hour. After 2 seconds, it'll be going 72 kilometres per hour. After 3 seconds, it'll be going 108 kilometres per hour. Okay? So if you drop something for 3 seconds, at the end of 3 seconds, it'll be doing about 100k, roughly. Okay? So 0 to 100 k's in 3 seconds. Any car can do that. Just push off the edge of a cliff. It'll do 0 to 100. It'll do 0 to 100 in 3 seconds, no problem. Yep. Okay. And it's guaranteed acceleration, no problem. So when I say that that'll do for any car, it doesn't matter whether it's a Mini or a Hummer. It's nothing to do with the mass. They'll go exactly the same. Yeah. So any 2 things that I let fall should go exactly the same, if what I'm telling you is the truth here. Okay? So if I drop, what do you got here? Is this anything breakable in here? I can use your bag. Okay, I've got a handbag. Okay, so if I start with a handbag, which is probably, I don't know, 20 times heavier than this pen, if I drop them both, they should both go exactly the same. Yeah, even though this was 20 times heavier than this one. We all believe that? Would we expect the heavy one to go faster? Yeah, let's assume not. They're both kind of aerodynamic. They're not aimed at a sheet of paper. If I drop a sheet of paper, maybe it would. Yep, but let's not go for that. So let's get enough, but a height here so we actually see what's happening. Oh, I can get right to the ceiling here. Awesome. This is the silliest room I've ever done. Okay, right. Okay, so if I'm telling you the truth, they should hit the ground at pretty much the same time. Ready, go. Yep. Certainly in terms of, there wasn't a cell phone in there, was it?
Maybe.
You said I could drop it before. You said I could drop it before we did it. Yeah. So things in Earth, things fall at the same rate, and the rate they're falling is 10 meters faster, 10 meters per second faster for every second that they fall. Yeah. And like Dylan said, air resistance will be an issue. So eventually the resistance of air will slow them down. You get terminal velocity. If you did it in a vacuum, they just keep on getting faster and faster and faster. And even if you did it in a vacuum, you could drop a feather and a lead ball. A feather and a cannonball in a vacuum would fall exactly the same. Yeah. So this is a really interesting story as well, is that up until Galileo, everyone had assumed that something that was twice as heavy would fall twice as fast. So that was it's obvious. It's got to be the case. Yeah? But physics wasn't an experimental science. The Greeks had started with it as a thinking. Yeah, that's how Greeks did physics. What do you think about that one? Have another cup of tea. Yeah, okay, yeah, let's think about it. And it was all about thinking and discussing and questioning philosophy, basically. Natural philosophy is what they called it. And no one thought about actually trying it out until Galileo. I'm not sure about this. And the story is that he went up to the top of the Leaning Tower of Pisa and dropped, because it's on a lean, so it's easy to drop stuff, and dropped a couple of a big cannonball and a small one off the top, and hit the ground at the same time. And he went, see, I told you. They went, whoa, that's an interesting way to do it, rather than just thinking about it. And sort of we have this like new idea of, like we did yesterday in class. You know? Some group I said to you, where you said, I think this will probably happen. And I went, I don't want to hear that. I want to hear that you've actually tested it and you've told me what's going to happen. You know what's happening because you've seen it. Yes, we have this like change in ways of thinking. Okay, so that's the meters per second is really important with that. We got to joules as being work, and it's making a force move a distance. Yep. So if I was to lift this box of paper, which is about 10 kgs, so that's how many newtons? 10 kilograms, roughly how many newtons? Yeah, well, equals mass times 10. So 10 kilograms times 10 is 100 newtons, okay? So this is about 100 newtons, this box. If I lift it 1 metre, I'm about there somewhere, I guess, I've done 100 joules. Okay? So that's 100 joules. I'm pretty good at 100 joules. I can just manage it without killing myself. So I'll call that 100 joules. It's probably a small metre, but who am I to quibble? So I'll call that about 100 joules. Rightio. Watt is watt. A watt. See, is there any difference between doing this? And I'll get a something for the camera. Let's get a space that we can work with. This is just for the. Yeah, there we go. Now we're seeing, aren't we? Here we go. Okay, so I'm going to do 100 joules of work, as demonstrated. Here we go. Thank you. Yeah. Well, thank you, Walter, for the round of applause. It was generous. Okay, so that was 100 joules of work. I'm now going to do 100 joules of work again. Ready? Here we go. Also, 100 joules worth of work. Didn't get quite the same applause that time. Obviously, there was something different. What was the difference? Speed. So one of them I did a lot faster than the other one. So if we're going to measure how fast we're doing work, that's what we call power. Okay, so a power is 1 joule every second. Okay, so to be doing 1 watt I have to do 1 joule every second. So if I took 1 second to lift that up, then I would be doing 100 watts. Okay, so it's 100 joules. From there to there is 100 joules. If I did that in 1 second, that's 100 watts. Okay, here's the challenge. I need someone that thinks that they can, has been to the gym a bit and thinks they've got a bit of, thinks they can beat a light bulb. And so a light bulb, standard light bulb, 100 watt light bulb. Okay, I mean, this disc is probably not a full metre, maybe it's 0.8 of a metre, so maybe we're talking about an 80 watt light bulb. So who can beat an 80 watt light bulb? James can beat 100 watt. Come here, James. James is going to demonstrate what a 100 watt light bulb looks like. Okay, so here's the game, James. You've got to get the box from the floor. There you go, he's got to squeeze past, so we can get him past. So you've got to get the box from the floor to the level of the disc. So it doesn't have to go on the disc, it's got to clear the disc. And Natasha, because she's got the best view, is going to count out loud how many times the box clears the disc. Okay, so it's the bottom. So lift it up, James. Just quietly, just once, quietly. So you've got to get it. That's over the disc now, isn't it? So if it gets over the disc, you yell out 1, and then it's got to touch the floor again, and then come up again, and you yell out 2. Someone else is timing. Who's got to watch? Someone's got to watch. Someone's got a cell phone with a watch. James is the only man with a cell phone. We can't have that. Who's got? Here we go. Connor's the timer. Okay, so you go 1 minute. You're going to see if you can beat a light bulb for 1 minute. Okay, so you're going to do it once every second for 1 minute. That's 60 seconds. So you've got 1 minute to get that box above the top of the disc 60 times. Connor's going to give you a countdown and call start, and Natasha's going to count out loud so everyone can hear how many times the box clears the disc. You understand the rules? Yep. Everybody happy with what you're doing? Let's see James do a light bulb.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47.
47. Awesome effort, James. Well done, well done. Yeah, round of applause for James. 47. Awesome. So that was 47 in a minute. Yep. Okay, so he wasn't quite, he did 60 in a minute to be up to a 100 watt light bulb. So James was maybe about a 80 watt light bulb. And if that wasn't quite a metre, maybe a 75 watt light bulb. So somewhere around about that. That's what you get when you turn on your light bulb. It's doing that amount of stuff. Okay? And you pay by kilowatt hours. So when they charge you for your electricity, it's in kilowatt hours. So that's 1,000 watts, not 100 watts that James was doing. So you have 10 Jameses doing that for an hour. Or maybe one James doing it for 10 hours, and the power company charges you 20 cents. So would you do that, James? Would you do that for 10 hours for 20 cents? Seems like a pretty good deal to me. That's what you should be able to do if you get 100% efficiency with your power. You should be able to do that. Obviously, you can't get 100% efficiency, but that's what. It's quite hard work, isn't it, James? Yeah, it certainly feel like it. Yeah. Top athletes, cyclists, Tour de France. So we won't argue whether there's too many steroids involved or not. Can output about 300 watts for a reasonable period. Sort of the human capacity is somewhere in that ballpark. Right, so that's a watt. Really, really interesting one to have seen working.